All right. Good morning, everyone. Welcome back to Physical Geology 1403. This is lecture 7. This marks the halfway point in the semester, as far as lectures are concerned, anyway. This is the last piece of content that you will get for Module 1, which means that the next time we meet will be our, bless you, Exam 1 review. Your exam will open as soon as you're done with the review session. So for those of you that are here live, synchronous with this schedule that I'm teaching right now, we are going to be meeting on Thursday. Come prepared with questions. That's 2 days from now. Come prepared with questions because all of my exam reviews are based entirely off of the questions you bring. If no one asks questions, we have a very short review. Okay. Now, for those of you watching this online, hopefully you took note of this when I mentioned it last week, but you need to send me your list of questions no later than tomorrow night. That is Wednesday the 5th. Tomorrow's the 5th, right? The evening of Wednesday, February 5th. If you send them to me the morning of, I may not see them before I start the exam review. So please try and get them to me no later than Wednesday night. The more questions we have, the better the conversation, the better the review will be for everyone. So where do your questions come from then? Well, your notes. Start looking through your notes over the last 6 lectures and notes for today, right? So there will be 7 lectures worth of notes that you can look at. And from those notes, see what you're comfortable with and what you're not comfortable with. If there's any part that you're looking at, you're like, he said something about Bowen's reaction series, and I don't really remember what that was, and I didn't write it down. Make note of that as something to ask a question about, okay? If I say it in a lecture, it's worth having in your notes, okay? There won't be any rock or mineral identification on this exam, okay? That's for the lab exam. You're still a few weeks away from that. This is all lecture related. Now, I do reserve the right to reference things from lab, like properties and things like that, but I won't ask you to identify anything. All right? I'll give you more information about the exam on Thursday morning. I'll give you all of the stats and what to expect and everything there. Just for now, expect to bring your questions Thursday morning so we can have a good discussion. Sound good? I think that's unlocked, right? Yeah, it is. Good morning. Okay. Any questions about anything at all? Anything in particular? Nothing we want to talk about? Nothing in the world that's captured your attention in the last 5 days? Huh?
Oh, yeah.
Say that again. Is this sports? Yeah, I have absolutely no idea. I don't follow most sports, and basketball is probably the one I follow the least. Sorry. I'm so sorry. I know I just dropped a couple of consideration points in your head, but yeah, sorry. Basketball, I've never really enjoyed watching or playing. I am fully a rugby, tennis, football to play. I prefer playing football than watching football, but rugby, I can watch that all day or play it all day. Yeah. Okay. Well, I'm sure that's exciting for you.
Oh.
Well, it doesn't have to be good to be exciting, right? Bad things can be exciting too. All right. Anything else? No? Okay. Well, then let's begin. Today we are talking about metamorphism and metamorphic rocks. That last section of the rock cycle we have not discussed yet. Today we complete it. Okay. So, right off the bat, let's talk about this picture. Describe to me what you see. Rocks. Excellent observation. Now describe them. They're curvy. What do you mean by curvy? What is curvy? The layers are doing what? You said curving. Huh? Okay, so they're curving in some way. Sure, we got some curvy layers. What else? Anyone want to elaborate on that point at all? Add to it? Argue it? Gathering data and hypothesizing. This is part of the scientific method, right? Any additional words you want to add to the observation?
Is it covered in moss?
Sorry, what?
Is it covered in, is that moss?
Well, there's definitely vegetation on it. Yeah, this is a pretty high up aerial view. What were you saying, Anthony?
I was going to say, was it caused by weathering? Like over time?
Was what caused by weathering over time? The curves of the rock, excellent hypothesis. Incorrect, but excellent hypothesis. No, we can tell that this was weathered, though, can we not? Yeah, this is definitely rock that is being weathered at this moment and probably has been weathered for some time. The curves, as you've been calling them, are independent of that fact, though. Now, we actually have a name for these curves. They are called folds. This is folded rock. What you're looking at here is the product of metamorphism. Our previously flat, nice linear layers of rock, as they were deposited, are no longer flat and linear and horizontally placed on top of each other. They're curved, as you said, but folded is the correct term here. So we're going to talk about that today. Metamorphism is any transformation that occurs in a solid. Can you think of another situation where the term metamorphism or a metamorphosis is applied? Oh, yeah, there are some bugs that go through metamorphosis. Butterfly, classic example, right? Caterpillar goes in a cocoon, butterfly comes out. Metamorphosis, it is a transformation of a solid, okay? This means that at no point does it enter a liquid state. It remains a solid the whole time, though its physical characteristics may change and its chemistry may change. Still stays a solid, though. Now, in your parent rock, which is what we call, the rock before it goes through metamorphism, you're going to see a difference in your texture, minerals, and the chemistry often as a result of going through metamorphism. And this can vary. The variation comes dominantly through a couple of factors. Heat, pressure, volatile content like water. We'll talk about each one of these today. But it can be anything from a very subtle change, like you can barely even tell that it's been metamorphosed whatsoever, or a change so intense that it doesn't even resemble the parent rock anymore. So the factors that influence metamorphism. Heat. Remind me what heat is. It is a form of energy. And when I put energy into a system, what's it going to do to the particles in that system? Excite them. Thank you. And so they start to vibrate. Remember, we talked about this a few lectures ago. When you vibrate particles too fast, what do? What happens to the bonds? Huh? Yeah, they weaken and fall apart. Yes. We call that melting. But if you excite them just enough so that they don't fall apart, they don't melt, they're simply more likely to change orientation or detach here and reattach over there, change things in the chemical composition or the chemical layout. That's metamorphism, okay? Think of it as, y'all ever gotten like a Hershey's chocolate bar and you put it on in your freezer, right? It gets nice and hard. I actually prefer my chocolate frozen. I like eating frozen chocolate. It's much better that way. Reese's peanut butter cups too, sue me. Okay, so, but it's hard and brittle, right? But what happens if instead I put it on my car dash for about 5 minutes and then I take it off? It's not quite melted. It's not like a goopy sack of melted chocolate now, but it is squishy, you know, it's flexible. It has not yet become a liquid, but it is a more malleable solid, okay? Think of that as kind of the metamorphism zone. Okay, my solid is still a solid. It has simply become more malleable, and the bonds within it are changing. Still bonded, but a little more flexible than they were before. So we get, as a result of this, recrystallization of the minerals. So often what this will mean is we will get larger minerals where before we had smaller ones. For example, if I have a shale and I metamorphose it, that shale is usually made out of clay and silt-sized particles of the mineral clay. Okay, remember that first context I used, clay is anything smaller than 1/256th of a millimeter. And then the second way that I use that word clay, as far as the content is concerned, that is a secondary mineral produced by the weathering of feldspar. Two different meanings of the word clay there. Okay, so we've got clay-sized clay particles, right? And those will metamorphose into usually larger visible grains of mica. Okay, that's one example. Now, why would minerals, new, larger, different minerals form as a result of this? What is happening here? Why would this happen? Why would they change their state?
Would they compress on themselves?
There's definitely compression here. We'll talk about pressure here in a minute. But I'm asking the simple, I guess you could call it philosophical question of why these things are changing at all.
Stability.
It's seeking stability. Remember, for the same reason why olivine, which is formed deep underground under high heat and high pressure, breaks down so easily at the surface conditions under low heat and low pressure, it is no longer in the situation that it formed in. Therefore, it is less stable. For the same reason, clays which are stable at surface conditions, once subjected to high heat and pressure, are going to recrystallize into a new mineral to seek stability. Same driving force here. In general, things in nature are seeking a state of stability. Okay. Okay. Now, where does this heat come from? Well, there are a couple of ways we can get it. Principally, the geothermal gradient, though. Remember the geothermal gradient? Someone tell me what that is.
It gets hotter as you go further towards the core.
Yeah, it gets hotter the deeper you go underground. The geothermal gradient is the rate at which heat increases the deeper you go underground. AKA, go deeper, get hotter, right? Now, this occurs at about 25 degrees Celsius per kilometer of depth. Do you remember, now hopefully you all wrote this down, do you remember what the interval for diagenesis was that we discussed last time when we learned about sedimentary rocks? What is the temperature interval for diagenesis? It occurs between 150 degrees Celsius and 200 degrees Celsius. Now, diagenesis is any change that occurs to the sediment after deposition but before metamorphism, which means, according to that definition I gave you, since it happens before metamorphism and it ends at 200 degrees Celsius, metamorphism must begin at 200 degrees Celsius, right? What depth is that according to the geothermal gradient? If I am increasing my temperature by 25 degrees Celsius per kilometer, how deep do I have to go to reach 200 degrees Celsius?
8 kilometers.
8 kilometers. Okay, so under normal conditions, if we only allow the geothermal gradient and normal pressure conditions to exist in our situation, in our theoretical situation here, then we reach 200 degrees Celsius at 8 kilometers of depth, and right there is where metamorphism can begin. Now, there are some exceptions to that. What if I'm at a subducting plate boundary? Well, I'm going to have higher heat and higher pressure closer to the surface because of the compression of those two plates, right? So I don't have to be 8 kilometers deep for metamorphism to happen. So that's an exception. In normal conditions, like a burial situation, though, where I'm out in the ocean or I'm in a floodplain or something like that, where layer upon layer sediment is deposited on itself, things get buried deep enough, yeah, they'll reach that temperature and pressure threshold and they will start to metamorphose, okay? And then also if I have any magma that's rising from underground, it's going to bring that heat with it, right? It's melting its way up through rock, but it doesn't melt all the rock, only the rock that's in direct contact with it. What about the rock a little bit further away? It's still getting heated up because of proximity, but it's not directly melting. That rock gets metamorphosed. So there are a few exceptions to this 8-kilometer rule, but according to the rate of the geothermal gradient, 8 kilometers is the depth at which it would begin under normal circumstances. Okay. Now, there are a few things that can influence this as well. The fluids, how much water you have. If you have a lot of water, you'll get certain types of metamorphic rocks. If it is dehydrated rock that has lost a lot of water content, you'll get very different metamorphic rocks than you typically would as well, okay? So this product of having different metamorphic rocks form as a result of the absence or excess of water, we call this metasomatism. It's not really something we're going to dive a whole lot more into in the class, just something that's worth mentioning real quick. It's called metasomatism. The parent rock. The parent rock is a huge factor into what metamorphic rocks you can have. Okay. Let's see. Who has... What's in your backpack right now? Your computer? That's it?
Yeah.
No pens, no paper, no nothing? Just computers? Well, that's boring.
Yeah.
Miriam, is that your bag?
Yeah.
Yeah? What's in your bag right now?
Journals, my folders, and paper.
Journals, folders, paper. You got a ton of keychains. Is that lotion, CeraVe?
Yeah.
Nice. So you've got a bunch of stuff in your bag. If I dumped your bag in water, I won't. But if I did, if I just filled up a bathtub and chucked it in there, has the contents of your bag changed? It would get wet. So, I mean, there's a little water in there, but the contents that it had beforehand are still the same contents that it has after I put it in there, right? Right? Yeah. So if I have a rock that has, say, 7 minerals in it, and those minerals are all composed of a certain structure of atoms, then when I metamorphose that rock, it is still going to have the same ingredients there that it had before after the fact, right? The condition may have changed. I may have changed a little bit about the size, shape, orientation of all these things, but I still have the same ingredients that I had before. Miriam's bag still has lotion and notebooks and journals and pens and keychains and all of that, regardless of where I put it or what condition it's in. I can't just all of a sudden whip, I don't know, boron out of somewhere if I put something that has calcium, oxygen, and carbon in the situation, right? Boron won't come from anything. So the parent rock dictates what things get put into this equation. And a reorientation of those things will result in the new metamorphic rock. Now, let's say in that, if I were to take this example a little bit deeper, let's say instead of a bathtub full of water that I put Miriam's bag into, what if it's a bathtub full of ammonium nitrate? Don't breathe, right? But I'm adding totally different things to this equation. And if I were to heat that up, change things, I'll make it a different reaction as a result. I'm adding different things to this equation. Water can bring in different things to this equation, which is why metasomatism can occur. Okay. If I have groundwater that is rich in magnesium or groundwater that is rich in carbonic acid, I may be introducing something here that could result in different minerals as a consequence. Okay. Now let's talk about pressure. Pressure comes in two varieties as far as metamorphism is concerned. First off, there's confining pressure. Now, everyone close your eyes and just feel the air around you. I promise this isn't a hippie thing. Okay? Just feel the air. Can you feel the air pressure? I would be truly astonished if you could. You've spent, I don't know, 16 to decades of life feeling that, right? I'm not going to guess, right? Of life feeling this. Maybe when you were first born, it felt weird to be in the atmosphere, to have the atmospheric pressure. It was quite different from the womb, slightly different. Mostly the same, but slightly different. So it might have felt weird, but you don't remember that. For most of your life, you have gotten used to this. And so air pressure is it's not something that we recognize, and yet it is there, equally distributed on all parts of our body, depending on the elevation you're at. The air pressure at the top of Mount Everest is slightly different than the air pressure in Odessa, Texas. And yet, if I was standing on Everest, the air pressure would be equally distributed across my body as well, however different it is from here, okay? This is confining pressure. Equal pressures from all directions on a certain point in space, okay? Now, close your eyes again and imagine you're at the bottom of a 12-foot deep pool. You're just sitting there. Air's not a concern. Don't worry about it. What's breathing anyway? Who cares? Oxygen's killing us, right? Okay. At the bottom of that 12-foot deep end, can you feel the pressure of the water around you? Yes. And guess what? It's equally distributed across all parts of your body, right? That is the condition at that depth. That is confining pressure. So if I were to pick any random point in space, be that atmosphere or a mile underground, confining pressure is when I have equal pressure from all directions on that one point. Now, when this is occurring to a rock, this kind of pressure, confining pressure, can cause metamorphism. However, because it is equal in all directions, it won't cause any deformation of that rock. Right? I'm not going to get any of those nice folding things that we saw earlier as a result of confining pressure. Those folding features come from our second kind of pressure. This is called differential stress. To demonstrate this, I will need a volunteer. Who wants to help me out? Want to help me? No? You have the brace on? Claudia, can you help me out? No, you don't want to? Are your knee hurts? Well, I'm not going to argue with that. Who's going to help me out? All right, come on up. Are you going to fold me? I'm not going to fold you. No.
What do I just stand here?
You just stand there until I say otherwise. All right, so here we have 3 layers of rock. You take that end for me. We're just going to stretch it out.
This doesn't look like rock to me.
It doesn't look like rock to you?
No.
Well, you think you know what? You think you're a geologist now? You think you know what rock looks like? You take 3 weeks in my class, and you think you know more? No, I'm just kidding. All right. So here we have 3 layers of hypothetical rock. Okay. You can tell the difference between them, right? I've colored them. So differential stress is when I have unequal stress coming from different directions. So here, pull it tight. Let's make it nice and tight. Okay. Right now, I have 3 layers of flat rock, but let's assume that we have some tectonic forces at play here, which are causing directions of stress on the lateral plane, as far as the way you're looking at this frame of reference right now. So along this plane, I'm about to have tectonic stress pushing this way and that way. Can anyone think of a situation in which that might occur? Huh? What about a convergent plate boundary? 2 plates crunching into each other, right? Now watch what happens. Right now, here, hold it tight again. Right now we have 3 flat layers, but now these 2 directions of force, Marquez and I in this case, are going to take 1 step towards each other and watch what happens. What happened to our layers of rock? What do we call that?
They folded.
They folded. They fold up and they fold down. This is how metamorphism, this is a metamorphic force, this differential stress causes metamorphism. This is a product of that. The folding of layers of rock, deformation as a result of metamorphic stress, specifically differential stress, the second type. Okay, so we have confining pressure, equal force from all directions, and differential stress, unequal force from certain directions, causing folding and other deformations. Thank you. Okay. Any questions about the heat or pressure or what they do? All righty. So, some examples of what this can do to rocks. First of all, if I have layers of rock that have large grains in them, let's call them gravels. Okay, anything larger than 2 millimeters, right? That's like our gravels and upward, right? So if I have the large, easily seen grains, and I exert differential stress on them, they're going to deform. They're going to flatten out. Now, the last time I passed this around, someone broke it, which is why it's in 2 pieces, but you can put them together and see the nice, beautiful piece that it was before. You can see in this particular sample how my nice, well-formed, rounded, this was a conglomerate at one point, how these grains, what's happened to them? Okay, tell me that in words, Alyssa. They're squished. Excellent word choice. Okay, flattened, squished. Now, what force could have done that?
The force coming from the top and the bottom, or
So you just did right there with the cookies?
And what force did we call that? Now, convergence was an example of how it could happen. Differential stress, right? Differential stress has caused it to flatten. Now, how can I tell what direction that differential stress came from? That unequal force came from which direction? How could I tell? When Marquez and I took 1 step towards each other, our layers of flat rock folded. In what direction? Right, down in that case. It could also have gone up. It only went down because, gravity did that to the foam, our hypothetical rock, right? But it could also have gone up just as easily. As a matter of fact, we see them up and down fairly in evenly distribution, right? We usually see both of those things happening as pairs. But the deformation occurred perpendicular to the direction of stress applied. The rock, in our example, folded up and down, while the stress was applied from the left and right. Yeah? The same thing is true of this effect, this flattening effect. If I find this in a layer of rock, and I'm looking at the rock in its native situation, I have not removed the sample at all, and I see that they are flattened up and down, that tells me my pressure came from which direction relative to this orientation? Well, these are lengthened up and down, right? If I'm holding it like this, and I'm looking at it in an outcrop of rock, from which direction was the stress applied? Use words. Left and right, because the deformation is going to occur perpendicular to the direction of stress applied. If I have a ball of Play-Doh in my hands and I squish it, what direction does it deform? Up and down, even though my pressure is coming from the lateral, right? The side to side. It's going to deform up and down, right? Makes sense? Okay, I'm going to pass this around. It is already in two pieces, so please be careful with it. Now, here's another fun example. Let's piece this out. Here I have layers of rock. Now, this is a shale, okay? It's a metamorphosed shale. So I can see the bedding planes, the original bedding planes in my shale, right here. I have 4 distinct layers of shale here, but it's been metamorphosed. So while I can see the original bedding planes, I can also tell what direction is it preferentially breaking in. It's breaking like this. You can see that in the picture, right? It's shaving off in layers that way. But why? Wait a minute, why? Shale makes those nice flat layers as the clays get compressed, right? But those always go along the direction that they were deposited. So why, after I metamorphose this, is it now breaking at almost this 90-degree perpendicular angle to the original depositional layers? Ooh, say that again and elaborate.
It's getting squeezed that way by something holding it.
It got squeezed, but what stress did we call that? Say it louder. Differential stress. It is differential stress. Good teamwork here. Differential stress from what direction? Yeah, 90 degrees to whatever orientation they are in now, huh? So what happened to this? Just looking at this, I can tell a lot of the history of what happened to this rock. At some point, this shale experienced differential stress at 90 degrees to the angle at which those are all oriented now, causing the clays, I should say, to reorient themselves at 90 degrees to the pressure instead of where they were before. This is called foliation. We'll get more into foliation on the next couple of slides. But the last example that I want to show you is here we have a really deformed. It's doing something like that. Actually, it went even crazier because this is coming back over here, right? Doing this funky chicken dance here. Okay, why would my layers of rock look like that?
Something crazy was going on.
Something crazy was going on. What crazy thing?
It happened quickly.
What happened quickly?
An eruption or something.
This isn't an igneous rock. This is metamorphic rock. Not an earthquake. We're looking at folding. This one layer of rock was folded, right? But not only once, a bunch. So whatever this is was a folding event, right? But then let's say that I have, what happens if I take a layer of rock that's folded like this into the sine wave? And then I take this layer of rock, and then I have a larger, more intense folding event. This all folds around. So I end up with a larger fold that encompasses that previously folded layer. So I'm looking at multiple folding events when I'm looking at something like that. There is rock that is so ridiculously convolutedly folded, it looks like it's almost impossible to piece it out. That happens when you have, when you see that, you know something really intense happened there, right? That's a lot of differential stress under different situations over a long period of time. I guess I should probably erase all that too. All right. Now, foliation. Foliation is a metamorphic texture. When I talk about metamorphic textures, you can say it is foliated, non-foliated, or porphyroblastic. Foliated means that, or foliation is an alignment of parallel minerals that have formed perpendicular to the direction of stress applied, just like in that shale we just talked about. There are different degrees of foliation, and we usually differentiate them from each other based upon the rock they're most commonly associated with. For example, slaty foliation is commonly found in slate. Schistose foliation is commonly found in schist. Gneissic foliation is commonly found in gneiss. Talk more about each one of those here in a minute. Non-foliated rocks, that's pretty self-explanatory. If foliation is the result of differential stress in a metamorphic environment, non-foliated rocks must be the product of what kind of pressure?
Confining pressure.
Confining pressure. Yes, confining pressure makes non-foliated rocks. Differential stress makes foliated rocks, metamorphic rocks, right? And then porphyroblastic. Porphyroblastic is very similar to a word that we learned about in igneous rocks, porphyritic, right? May have sounded familiar there. In a porphyritic igneous rock, you have large grains and small grains. In a porphyroblastic metamorphic rock, you have large grains and small grains. But the difference is they are grown through the metamorphic process instead of through cooling magma. Cameron, stay with me here. Hi, right here. Hello. Thank you. All right. So this is a porphyroblastic metamorphic rock. This is a mica schist, which will make more sense in a little bit, with a very large, lovely garnet in there. This is a porphyroblastic metamorphic rock. That would be the texture of this rock because it has both those tiny grains and a very large crystal in this case. Okay. Pass that around real quick. So let's talk about foliation. There are different types of foliation. All of them are formed by differential stress. The planar alignment of minerals perpendicular to the direction of differential stress is how you should think of foliation. So this can happen a couple of different ways. I can have a flattening of those minerals, like what we saw in the sample I passed around not long ago. It's probably still making its way around. Yeah, right there. Okay. I get that flattening of minerals. I can have a reorientation of minerals. If I've randomly oriented sodium feldspars and amphiboles in, say, a diorite, they will reorient themselves and make a planar arrangement to make something that looks like that. Matter of fact, here you go. Look at this. Here I have a diorite, sodium feldspar, amphibole. Randomly grown crystals from the magma, right? But if I subject this to differential stress and heat, they will reorient themselves in what direction? Not always up and down. That's relative, right? But they will always be perpendicular to the direction of applied stress. And I get this. The same mineral content. You can see that, right? Same minerals. But this one has become foliated. Okay? And then there's recrystallization. So my minerals partially dissolute from each other, right? They're more likely to break apart and go over there to join that bond without ever having become a true liquid, right? Or a liquid at all. But you get newly formed minerals as a consequence, and those new minerals are already oriented to the direction of stress, perpendicular to the direction of stress, okay? So there's the flattening, the recrystallization, and the reorientation. That's how you can get this. Pass this around.
Yes.
Okay. Now let's talk about the different degrees of foliation. With slaty foliation, this usually happens when you have a low degree of metamorphism. I get very flat, thin layers as a consequence. Okay, this is slate. You ever heard the term slate? In Minecraft, of course. As a metaphor. Yeah, wipe the slate clean. I love that. I was about to bring this up. Do you know where the term wipe the slate clean comes from? I mean, yeah, but very specific flat surface. Chalkboards. Chalkboards used to be made out of slate. So when you say wipe the slate clean, what they're talking about is when you would have to take a damp rag and wipe the chalk off of your chalkboard. Yeah, that's where that comes from. Now, we don't make chalkboards out of slate anymore. It's a synthetic material that is easier to clean, and you don't have to, like, it's meant to, like, you can use, like, cleaning supplies on it and stuff. We don't really use slate anymore for that, but that's where that term comes from. But why did we use it as chalkboards? Because you get very fine, very flat surfaces in slate. This is slatey cleavage. You might see it termed as cleavage in some places. I'd rather you didn't use it as cleavage because we learned cleavage as a mineral term. So we're going to call it slatey foliation. Okay. Slatey foliation here. Okay. Very thin, flat layers. Our next is schistose foliation, which we commonly find in medium grade metamorphism with rocks like schist, like this. So it's still largely flat, but there's some undulating to it. Okay. I apologize if that word disturbs people. I hear that's one of the words. You know how there are words that like people find disturbing? Like a lot of people can't stand the word moist and stuff like that, right? Undulate is another one of those words. I apologize if I'm triggering anyone right now. Huh?
Say it again.
Undulate.
Sexy word.
It's a sexy word. Should I start an ASMR channel where I just say undulate? No? Okay. So yeah, there's some waviness to this. Okay. It's a schistose foliation. Medium grade foliation. So if I have just a little bit of differential stress, a little bit of heat, I'm going to end up with slatey foliation. A little bit more, I'm going to end up with schistose foliation. Okay. And then our final grade, actually I already started passing it around, is gneissic. Remember the one should still be making its way around the table. I passed this around earlier. But this is gneissic foliation. This is high grade. Yeah, Daisy has it right now. This is high grade metamorphism. Intense differential stress and heat are going to make this. And we commonly find this in the rock called gneiss. Gneiss, pronounced nice. She's handing you a rock. Okay. Let's see. Is there anything else I want to mention about foliation? It doesn't always come as layers. For example, in that gneiss that's getting passed around right now, you'll notice that we don't actually have layers. They kind of look like it at first glance, but they're more like bands of minerals. See how this black layer right here isn't actually a layer. It stops here and stops here. And this one's kind of stretched out like that, but it doesn't go past that. They aren't actually layers. These are bands. These are smeared minerals. Okay, like if I could take a mineral and subject it to so much heat and pressure that it gets kind of squished and stretched, like smeared across wherever it was in that rock at the time, that's what this is. Okay, not really a layered effect. Now, with non-foliated rocks, you're going to differentiate those by things like crystal size, content of like what minerals it's made out of. Limestone becomes marble. Marble is the metamorphic equivalent of limestone. It comes from that. You can get quartzite from quartz sandstone. We'll talk about all of these, but like with the Miriam's backpack example, you can only have in your rock whatever you put in there to begin with, right? I can't put her backpack in the tub and then pull it out an hour later and it's full of $1 million. That's not how it works. Okay. And then there's porphyroblastic minerals. Porphyroblastic minerals are commonly schist. They're usually schists or a type of pre-schist called phyllite. These can occur in some gneisses as well, where large crystals grow, like the one that had a garnet in it, like Abigail has over here, okay? The one that had the large garnet in it. Those usually form out of whatever is left over in your rock, okay? So as your schist is forming, or as your metamorphic rock is forming, extra stuff kind of gets tossed into whatever these porphyroblastic minerals are. And they can be garnets, starlites, andalusites. I have found some beautiful porphyroblastic marble before. I was out in Utah and found a very thin layer of metamorphosed limestone. So it was marble, but it was low grade. Like it was just falling apart really crumbly, but it was full of garnets, beautiful, like greenish red garnets. Like it had both colors in it. So I took a whole bunch of it, and marble's made out of what? Limestone, which is made out of what? Calcite. Good. Calcite dissolves in. That's true, it does, but that would take a long time. Hydrochloric acid. You remember how we put some on there, made right? So I took all of that marble and I put it in a tub, and I filled that tub with hydrochloric acid, and it looked like a witch's cauldron for like a day and a half. There's bubbling. But by the time it was done, all the marble had been dissolved, and I just had a tub full of beautiful garnets. Yeah, the things you know how to do when you learn geology, right? So my intent was I was going to make a necklace, a garnet necklace for my wife out of it. That was about 8 years ago. I still have that intent. Someday I'll get around to it. All right. So after you have found your texture and your grain size, which works the same way that it did with sedimentary rocks, right? We're just looking at how large they are. The composition, how do you figure that out? Well, because you've studied minerals, right? You know how to test for minerals and figure out what minerals there are. Some fizz with acid, some scratch glass, some have certain colors and cleavages, yada, yada. Then you can find your rock name. It's the same way that we've been identifying every other mineral in every other lab, okay? Everything, every classification of rock has its own properties that you find. Now, let's talk about some of the more common metamorphic rocks that you're going to encounter in this class and out. Slate. Slate is the result of lightly metamorphosed shales most of the time. So our clay and silt sized particles are still mostly clay and silt sized, but instead of being randomly oriented, they are now reoriented in what direction? Is slate foliated or non-foliated? It's foliated. That's why it has that nice flat layering to it, right? But in what orientation are all those clays oriented? Relative to what? Not the bedrock. That's relative to the surface they were deposited on is where they were oriented when it was shale. But now it is slate. It has been foliated, which means that those clays are now oriented perpendicular to the direction of applied stress. Okay, whatever that was. Just like shales, they get their color based on what they're made out of. Red shales will often result in red slate. Black shales, black slate, so on and so forth. Excess iron, excess organic content, excess chlorite. Okay. So I already passed around that slate, so I don't think I need to pass it around again. But this next one, phyllite. Phyllite. If I take my slate and I metamorphose it a little bit more, I'm going to get phyllite. Phyllite has still very small minerals. They've just gotten a little bit larger. They've gotten large enough that the rock itself takes on this sort of glossy, shiny appearance because my clays are starting to turn into micas. Still too small for me to really see, but enough of them have formed that it takes on this shiny, glossy surface luster. When you look at it, you can also see that my layers are not really perfectly flat anymore either, like in that slate. They've taken on a sort of curvature to them. We're working towards that schist stage. So we've gone slate with light metamorphism, slightly more metamorphism, you end up with a phyllite. Then,
What's the name after some guy named Phil?
no. Do you usually spell Phil with a Y?
Yeah.
You do. Okay, cool.
I've seen the guy.
You just always have to be different. It's a basketball player, isn't it?
Definitely.
I would not be surprised if there's some basketball players have the craziest names. You ever watch Key and Peele? You know the East-West Bowl names? Those are some of the funniest names. All right. Schist is that, I already passed that around as well. Schist is that medium grade metamorphism rock. So if I take my phyllite and I metamorphose it a little bit more, I'm going to end up with schist. I've got large, well-formed micas. That's why it's so shiny. You can even see the mica crystals in there. You can also see other stuff in there. As I pass this around, you may have noticed those black dots that you see in there. Those are tiny little garnets. So not only is this a schist, it's a porphyroblastic schist. Oh, I can both. It is both porphyroblastic and foliated. Ah, and here's the kick. Okay, here's the catch. I name schists based off of what's in them and how they're made. There isn't really a name like phyllite. It's that this is a schist, but what kind of schist is it? Well, there are so many varieties of them that we literally just call them based on whatever we see in them. So because I can tell most of the crystals in this are muscovite mica, but it also has garnets. It is foliated, but it also has porphyroblastic. It's also porphyroblastic. I would call this a porphyroblastic muscovite mica garnet schist. Literally, that's its name. It's what? It is a mouthful. There are some schists that have so many things going on. It's just like, we have lots of long names in geology, in case you haven't been able to tell. So, I mean, a lot of people just look at this and go, yeah, it's a schist, because they don't want to write it out. But if I was writing a paper on it, I would have to be very specific, right? Have I told you about carbon dating? You ever heard the term carbon dating? It's a very oversimplified term for radiometric dating. Like, carbon only works to about 50,000 years back to date things. So anything that's like dinosaurs and that, people may use shorthand carbon dating. The actual term is in situ ablation multi-collectively coupled plasma mass spectrometry. But no one wants to say that. So even though we aren't measuring carbon, a lot of people just say carbon dating, right? Science, we have problems. Yeah.
Why does that look like somebody took some shiny ranch and just,
Like ranch dressing?
yeah,
You're hungry, brother.
I
That rock looks like ranch dressing. It's because you're hungry.
probably.
I can't blame you either.
Have some good chicken tacos for my mom for lunch.
Ooh, you got chicken tacos? I have my daily special. 2 hard-boiled eggs and some cashews.
Ooh,
Yes.
good luck with that.
No, I alternate. It depends. So I'll do hard-boiled eggs or I'll do raw broccoli and almond butter. Yeah. Well, I mean, yeah, that's just, this is kind of how I've worked it out, right? because I try and stay fit because I do not want to ever reach the point. I made a commitment when I had kids. I always want to be the kind of dad who takes care of himself to the point where I can do anything that my kids want to do. You want to go hike a mountain? I'm there with you. You want to go bike to the next city over? I'm there. You want to play football? Whatever, right? So I've worked hard to keep myself there, and it's not easy in a world that tries to force feed you preservatives and stuff all the time, right? So the way I've worked out for myself is I don't usually have breakfast. And then for lunch, it's usually something that's really fiber and protein rich like that, right? And then for dinner, I just kind of have whatever. It's usually some sort of chicken or fish, potatoes, onions, some sort of sauce, something like that. But I don't pay as much attention to what I eat for dinner because that's social. I'm there with my family. I'll eat whatever we make, right? But for the other 2 meals of the day, I'm very, very meticulous about what I eat and how much because I don't want to, lose control of myself. Anyways, that was a tangent. Beside the point. Chicken tacos sound really good. All right. Yes.
I was wanting to know what type of rock is in Fort Davis, all those mountains.
In
I know
Fort
it's a lot of
Davis.
topics, but
Yeah.
you've never been to Fort Davis?
I've been once. I remember
It's like
looking
red
into
rock.
this.
It's like reddish, brownish rock. And like all
Yeah.
the mountains.
Yeah. I remember looking into this a few years ago, but it's been a while since I thought about it. Can I look into it after we're done with the lecture? Let's finish the lecture, and then I'm going to look at that because now that you've brought it up, it bothers me that I don't remember since I did look into it at one point. So I'm gonna think about that. I'm gonna look into it when we're done. Okay. If they're reddish brownish.
And they have like rounded shapes, like a bunch of rocks stacked against like rounded rocks stacked. Have a lot of
If
different-
there's a bunch of rounded rocks, my guess would probably be sandstone because they'll weather into rounded shapes a lot of the time when after exposure to wind, but a lot of rocks will. So again, I'll have to look into that. Okay, nice. High grade metamorphism. I take that schist and I metamorphose the crap out of it. Okay. It's right smack dab in the middle of that mountain range, right? It's getting metamorphosed hard. You get nice. Okay. Again, you don't really get layers here. There are these discontinuous bands of color as each mineral crystal kind of got squished and smeared flatter and flatter and flatter. Okay, so that is metamorphic rocks. That is foliated rocks. Non-foliated metamorphic rocks. Marble metamorphosed limestone, aka made out of calcite. Here we have some marble. Just like with limestone, just like with calcite. Drop acid on it, it'll fizz. Now you've got large crystals here. Like I said, metamorphism tends to cause small crystals to recrystallize into larger crystals. These are large crystals of calcite that have interlocked here. Marble is often used for building, right? It's construction material. It's used for decoration. It's soft, so it's easy to carve. A lot of statues, like like Michelangelo and a whole bunch of sculptors, famous sculptors, worked in marble because it is soft and easy to chip away pieces from. Okay, and then smooth down and polish after you're done. Okay, as marble. Now, the marble gets its color. There's lots of different wild colors of marble. Gets its color from whatever was in there when it was a sedimentary rock. Okay, very few limestones are perfect 100% just limestone. Sometimes there's some sand in there. Sometimes there's some clays in there, right? Especially if you're in a transition zone where I'm out deep enough that I deposit clays, but a little bit closer to shore, I'm making limestone because I'm depositing a whole bunch of living organism material, right? But what about in that transition zone between the two areas? I'm going to get both limestones and clays out there. And where there's that intermixing, my resulting marble, if it gets metamorphosed, is going to have different colorations based on what extra stuff was in there. So if I see bands of brown, darker yellows like this, that might mean that there was some clay mixed in there in the limestone. That one I'm passing around right now is pink. There might be just a little bit of potassium feldspar in there, perhaps, or some iron.
The color of that one and the look of that one reminds me of those salt lamps.
Yeah, the Himalayan rock salt lamps. I have a whole bunch of Himalayan salt, including a lamp in my office. I do lick it sometimes. Sometimes I just need some salt. Okay. Quartzite. Quartzite is what happens when I have a quartz sandstone and I metamorphose it. And all of my sand grains, my sand quartz grains fuse together and I get quartzite. Now, again, just like the marble, the color is based off of whatever was in there. So a purple quartzite probably was a red sandstone, the oxidized iron, right? But every now and then, this isn't usually the case. With metamorphic rocks, the process of metamorphism usually destroys a whole bunch of sedimentary structures, like fossils. But sometimes, like in this particular one, you can see that darker line of purple right there. That's an old bending plane. So every now and then, it's rare, but structures are preserved. Again, it's made out of quartz. That will scratch glass, just like a large quartz crystal would. I don't have slides for these, but I do want to go over them real quick. A few more non-foliated metamorphic rocks. When conglomerate gets metamorphosed, does anyone want to guess what the name for that would be? It's super original. You ready for this? Metaconglomerate. Yeah. Right? Metaconglomerate literally just looks like a conglomerate, except all the pieces have been fused together instead of compressed together. Okay? Now, I told you what happens if I take a fine-grained sedimentary rock like a shale and I metamorphose it in differential stress. I end up with a
Slate.
Yeah, slate. Good. Under differential stress, that's true. But what happens if I take my shale or my mudstone or my siltstone or whatever it is, whichever mudstone, flavor of the week, right? Whichever one I'm talking about, and I subject it to confining pressure instead of differential stress. I get hornfels. 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 It's literally just a baked mudstone. Okay? It's like a brick. It's harder, denser than the shale was before, but it is not foliated. Okay? That is hornfels. Contact metamorphism is what I call it when a localized area of metamorphism takes effect. That is not a very large, broad area. A very small, relatively speaking, area is metamorphosed. The most common reason why this happens is a rising body of magma. Like I said earlier, the rock that magma encounters is going to be melted and incorporated into it. But what about the rock in proximity, around it? It's going to get metamorphosed instead of melted because it's under a lot of heat and pressure. However, what kind of pressure? Do you think that a rising magma chamber is going to create differential stress? Is it going to cause unequal stress?
Yes.
Tell me why yes.
It would change the pressure.
Well, tell me why. Argue your point. Does anyone want to raise counterpoint? Okay, Ray. The heat definitely is a given, but the pressure is what's in question here. Is it confining pressure or differential stress? Let's say there was no differential stress there to begin with. Would it introduce differential stress now by simply rising up to that area? Is it pushing its way up or is it melting its way up? It's melting its way up. It's not really shoving any rock aside, is it? There isn't going to be any differential stress. We are still going to have confining pressure, but we are going to have all that heat. So let's say that I have shale, limestone, quartz sandstone, and then more shale, and my body of magma rises up here. What are my resulting metamorphic rocks going to be? Shale will become? Yeah, hornfels. Why not slate? Because slate is formed from differential stress, and we are working with confining pressure in this example. Limestone becomes? Marble. Quartzite? Or sorry, quartz sandstone. Gave that one away, right? Quartz sandstone, and then shale up here. Hornfels. Good. So I'm going to have a halo or a thick band of metamorphosed rock around this magma chamber form. And once that magma chamber cools down, that metamorphosed rock is still there. Sometimes this gets exposed at the surface and we can see it. It's really cool. This is a mountain range in New Zealand, I believe, where you can see this diorite igneous pluton down here. This is the old magma chamber. And on top of it, this darker rock is that zone of metamorphosed material. I believe this is hornfels, if I remember correctly. Okay? But this is a whole bunch of metamorphosed rock sitting on top of this pluton. It's called a roof pendant, also known as a metamorphic aureole. So that is contact metamorphism. Magma metamorphosing something in proximity to it. Hydrothermal metamorphism happens when water encounters something that is hot enough to be metamorphosed. So a good example of this is at a divergent plate boundary underwater, say the North Atlantic Ridge or the Mid-Atlantic Ridge, whatever, any mid-ocean ridge, okay? It's underwater, and so you're going to have water seeping down through that thin crust, right? And encountering the super hot rock down here. And as it is forming and metamorphosing under those conditions, that water is going to strip away some metals, as water does, okay? It pulls away some of those metals, carries it away. The super hot water is going to carry all that metal away, and you're going to end up with metamorphic rocks where you wouldn't have before. Talc schist, for example, is what happens if you metamorphose a basalt as it is forming and you strip away its metals. Okay, so you'll end up with talc schist down there, and those metals. What happens to those metals? This super hot water wants to go up, right? It's seeking for lower pressure. It should be steam at these temperatures, but it can't be. So it's zooming up out of the crust, and when it gets out of the crust, what does it find? A super dark, super cold bottom of the ocean. And all of those dissolved metals in that superheated water instantly precipitate. You ever watched the Discovery Channel or maybe Animal Planet documentary about the bottom of the ocean? No? If you ever have, they probably have shown you these vents that are spewing out all that material. They call these black smokers a lot of the time. Okay? And it does look like smoke, to be true. To be fair, it does look like smoke that's being spewed out of the bottom of the ocean. It is not smoke, however. This is water we're talking about. That cloud of gray smoke is actually microscopic particles of metal from this process. The superheated water has come up out of the crust, met the extremely cold water, near freezing water at the bottom of the ocean, instantly precipitated, instantly formed crystals of those metals. And this is all that metal that's getting shot out of the bottom and then slowly sifting down to rest on the bottom of the ocean. because of the temperatures and because of the presence of these metals, a lot of fascinating life forms live down there. As a matter of fact, this is something that we talk about more in 1404, but a little precursor, I guess. It is theorized that life on Earth very well might have started around these vents because of the presence of water, lots and lots of chemically rich metals, okay? Like metals that are used to make the most basic forms of life. Phosphorus is required and is present here. You get iron and all sorts of different metals as a result of this process. But so many rich forms of life live down there. And guess what? None of it is photosynthetic. Most of the life that we have on Earth right now requires some form of access to the sun. These things don't. As a matter of fact, here's a fascinating thought. Because these things do not require whatsoever the presence of a sun, these things could live on any planet anywhere else, whether there's a sun or not. Which means, once we realize that, the parameters by which we consider life could exist somewhere else in the universe became vastly larger. There is a moon of Saturn called Enceladus. You ever heard of this? Enceladus is covered in about 10 kilometers of ice, a thick, thick layer of ice. But inside of that planet is liquid water. No sunlight has ever reached that water. And so for a long time, people thought, oh, well, there must not be anything alive. But the fact that we know that here on Earth, life has developed and can live in places without the sun, places like Enceladus or Europa or Titan that are covered in ice but have liquid water underneath of the surface, there could be things living down there that develop without ever needing photosynthesis or a similar sun-derived energy source. It's pretty cool to think about.
What you're saying is we could be invaded by aliens.
We could be invaded by aliens. I'm not going to argue that's not a possibility. A very low one, I would think. I love the subject of extraterrestrial life. If you guys are down for a tangent, I'm happy to talk about it, but I feel like I'm losing you. I'm seeing some drooping heads. Yeah.
What do you think the possibility of intelligent life living on those moons?
Intelligent life. Well, we have a very biased opinion on what intelligent means. Would you call a dolphin intelligent?
I agree.
Yeah. Would you
How
call
about sentient life, like like something like a dolphin?
What is the definition of sentient?
Feel things.
Feel things?
A dog, a rabbit, a bug. can be
Yeah,
something.
many things can feel things.
How about
Has a conscience.
Has a conscience? Interesting.
They have thoughts.
Thoughts?
Aren't just instincts.
Thoughts, not just instincts.
something like at least somewhat close to us?
So to be sentient, it needs to be something close to human. In form or in thought process?
I'd say thought process.
In thought process. Okay. I would, huh?
Technically, any living thing has some sort of knowledge, so that kind of reminds me of the quote, everyone's a genius, but if you judge a fish by its ability to climb a tree, it will spend its whole life being stupid.
Right. That's also a good point. We judge things based off of our own perspective, right? A fish can't climb a tree, and so, you know, what does that say about the fish, right? Dumb fish. Although, no, I'm not gonna. No. I was gonna say at one point our ancestors were fish, and now we can climb trees, but we're not gonna bring time into it. The ability to evolve is a totally separate subject.
That reminds me of, have you seen, that movie where they drop off an alien and he breaks down in the water and that's where all life form came?
Oh, you're talking about Prometheus.
Prometheus.
Yeah, that alien movie. Very
Yeah.
interesting stuff in that. Different subject though. Very interesting thought there. But
About the
origin of life.
Yeah.
Yeah. But the debate, or the question, I should say, not the debate, but the question was, do I think that there is other, did you say sentient or intelligent life? Intelligent life, absolutely, I believe. Because there's a difference between intelligence and what we might term sentience. Right?
Why I was thinking of
Computers
Star
can-
Wars terminology.
Oh, no worries, no worries. Intelligence, we make intelligent things. We have artificial intelligence now, right? It is, in fact, intelligent. It can parse data, draw a conclusion. It's going to take over the world? Okay, so we have a Skynet advocate. Where artificial intelligence takes us is a totally different subject. However, consider this. Based upon the number of planets we have found, there are, and we extrapolate that to the rest of the universe, there are about 70 pentillion planets in our universe. Now, if only 1/1,000,000,000, one out of every 1,000,000,000,000 of those planets has life on it, we're still talking 70 million planets with life on it, right? My math is right. That's a lot. Now, here's the issue. How far away are they? What does that, would we even be able to recognize that life if we saw it? There's a fascinating book written by Andy Weir called Project Hail Mary. That great book. Love his work. He wrote The Martian, if any of you are familiar with that story. But part of the plot is there's some forms of life that do not look anything like what we would have expected. They're actually mineral-based life forms. This is fascinating, right? They live in temperatures that would cook you and I to death in seconds. But it is the fact that they live in those temperatures that allows the particles in their bodies and their mineral construction to be mobile enough to allow for things like circulation and thought process, something similar to human neurons. Because those rocks that they are made out of are at a high enough temperature to allow for the mobilization of ions, their bodies can function in a way similar to biology, but not biology. It's a fascinating thought. Would we recognize life if we saw it? That's the tough question. I would venture not at first. So if we go somewhere like Enceladus or Europa, and we drill down through the ice, 10 kilometers through the ice, and we pull a sample of water out, and that sample of water looks like it has nothing in it, except maybe some weird chemical traces. And then hundreds of years down the road, we realize, wait, those chemical traces were the DNA or this a form of DNA that we could not recognize at first, but were evidence of life. I mean, I would not be surprised. As time goes on, our perspective broadens, right? Hundreds of years ago, people looked up at the sky and could not comprehend how much was out there. Every day we learn more about what's out there, and it's difficult for us to comprehend. I can't even imagine where we'll be in 100 years if we continue along this route. We may make intergalactic friends by then. Who knows? Science is continually advancing. Our understanding of where life could exist is continually advancing. It is perfectly likely that we are not the only living things in our solar system. Things could be living on those moons I've mentioned, Titan, Europa, and Enceladus. Things could have at one point lived on Mars. Heck, things could still live on Mars for all we know. We consider it a lifeless planet only because it is lacking a lot of the parameters for life that Earth has. Something could have adapted to live there. I don't know. I'll end on this thought. If life is so likely to exist everywhere else because of things like what we see living in these black smoker vents at the bottom of our own ocean, who's to say that life started here at all? If something could survive in a situation as hostile as boiling water without exposure to sun, then why couldn't it have arrived here on an asteroid from another planet? We have rocks on Earth that came from Mars. There have been collisions of asteroids on Mars so powerful that it blasted debris out into space, and some of that debris landed here. Vice versa too, by the way. Life could have started on Earth billions of years ago, and some of it could have gone to Mars. If we find fossils on Mars, this is the cool thing. If we go to Mars and we find fossils on Mars, and those fossils, those bacterial fossils, have DNA, then we know life started here or there. The question then would be where? Which one?
It'd be like the whole chicken conversation.
Right. Mars is a little older than Earth, as far as we can tell. But Earth has a much longer history of life because life has been here longer. That's not to say it didn't start there and come here on an asteroid life pod, right? These are all the sort of things that we're looking into, but I can see eyes glazing over. As much as this fascinates me, I understand that it's not terribly interesting to everyone else. So let's bring it back to center here. How did the hipster burn his tongue? He ate pizza before it was cool. No? Okay. Yeah, you can. All right. All right. Burial. Burial causes metamorphism because the stuff gets buried and reaches the geothermal gradient, right? This tends to happen over a larger area. Okay, so this is something that I would term a version of regional metamorphism, if you will. Okay. Basins, large basins, I'm talking like ocean-sized basins, lake-sized basins, valleys, they get buried over time. The stuff that was deposited first goes deeper and gets metamorphosed. Then you've got another version of regional metamorphism. This is the collision of mountain ranges, okay, or of continents to make mountain ranges. Great example of this, the Himalayas. Look at that atlas. Look how huge that Himalayan mountain range is. Massive. That whole thing is the consequence of the Indian subcontinent colliding with the Eurasian continent. Okay? So you have a huge mountain range, almost all of which is metamorphic rock because you have layer upon layer upon layer of continental rock and, by the way, oceanic rock that got squished between the two continents that get squeezed and folded and stretched and shoved high up in the sky. You think mountains are tall? You think Mount Everest is tall? It goes way deeper underground, folks. Okay? For every kilometer up in the sky it goes 2 kilometers down. Okay? Or more. Really, really, really deep. There's a lot of metamorphosed rock tied up in mountain ranges. That's where a lot of it forms. Okay. Fault zone metamorphism happens when you remember what I described the fault was? A fault is essentially a crack in the ground. We'll talk more about this in module 3. But a fault is a crack in the ground along which pressure builds until it slips. And when it slips, it releases an earthquake, right? So when that pressure is building up on that fault surface, it actually sometimes gets intense enough to cause metamorphism in that fault zone area, okay? And then there's another fascinating situation that you can get metamorphism. Excuse me. And that is impacts. Asteroids, meteorites will, the moment that they collide with Earth's surface, introduce so much heat and cause that moment of intense pressure so powerful that it will flash metamorphose the rock in a zone around it. So you'll get your crater, but the zone of rock around that crater and under it, by the way, will often become metamorphosed. We call that impactite. Okay. Do you guys know that we have a meteor crater here in town? You ever been? Okay. Well, for those of you that didn't know or haven't been, last year I was put on the Meteor Crater Advisory Committee by the city, which means that we have a new initiative that we put together last year where we want to put some money into the crater, make it a better tourist attraction. We're going to make it more interesting. We're going to put some educational stuff there. We're going to partner with some people, some companies, some organizations, hopefully get some federal funding so we can make it. It's a national historic landmark, and we want to treat it like that. We want it to be a nice place to visit instead of just a place you go and you're like, where is it? This is it? That's kind of what it is right now. We want to make it far more interesting than that because it's pretty cool. Do you know how many cities in the United States have a meteor crater that they can use like that? Very, very few. It's very rare. Okay. Why is it so rare, by the way, for us to find meteor craters? Sometimes they're that big. Does Mars have a lot of meteor craters?
Yes.
Yeah. Does the moon?
Yes.
What do we have that they don't?
Atmosphere.
Atmosphere, water. Earth is dynamic. Because it is so dynamic and constantly changing, old craters get washed away or weathered away quickly. So having one so close that is recent, it was 63,500 years ago that this thing hit, right? That's pretty recent, geologically speaking, and it's already worn away and filled in so much that we can hardly tell it's there. There are way more than that around the surface of our planet, but we can't see that they're there for most of them. Okay, so it's cool that we have one. Anyways, there is a zone of metamorphic rock around that one as well, is what I was getting at. All right, now, like I mentioned earlier, metamorphism increases intensity the longer it's metamorphosed and the closer it is to the source of metamorphism. So here in a mountain range, for example, right here off at the edge of my mountain range, my layer of shale, I'll keep with my example of shale. Let's say I have a layer of shale that goes all the way down here, okay? Over here near the foothills, it will be slate because it's this close to our zone of metamorphism. Over here, getting down deeper, okay, we're about to start, if I was climbing this mountain, I'd be about to start hiking up it, right? Phyllite. Down here, way deep, schist. And then down here at the very roots, where the metamorphism is the most intense, where the heat is the hottest and the pressure is the most intense, that's where we would get a gneiss. So our same layer of rock can go through this whole sequence depending on where it is in proximity to our metamorphic event. Okay? Or to the source of the metamorphic forces, I should say. It is a tectonic event. Okay, and then, right, okay, so this is just a chart that shows you what common minerals occur based upon the grade of metamorphism that it occurs in, and then what type of rock you'll get as a consequence. So here you can see we start with our slate, and then we end up with our gneiss, and what happens beyond that? What happens if we heat our rock up too much? It melts. Now, what happens? You learned about differential melting rates, right? Yeah. Some minerals melt at lower temperatures than others. What happens? If I take a rock and I metamorphose it intense and I make that gneiss, but that gneiss starts to melt. Some of the minerals melt, but not all of them. Then we end up with a rock called a migmatite. So here you can see our nice folded layers, right? And when you look at the layers at these black minerals, they are foliated, right? But what do you notice about the lighter, like these white and pink minerals? What? They're not. I mean, they are in folded orientation. Come on, camera, stay with me. But what about the minerals themselves? Describe those pink and light minerals for me. Do they appear flat? If you had to guess, what kind of rock would you say that is? Say it louder. Granite. Awesome job. Okay. Yes. What we are looking at here, folks, in this migmatite is foliated, folded amphibole crystals that never melted. Still in their metamorphic orientation. Still a metamorphic rock as far as those amphiboles are concerned. But the quartz and feldspar that was in this rock did melt. They got hot enough to melt. And what happens when they cool back down? They make a what? Igneous rock. No longer metamorphic. Why? Because it melted. Any rock that comes from magma is igneous. So you keep saying granite. Yes, basically what we have here are layers of granite and layers of metamorphic gneiss. This is called a migmatite. Isn't that cool?
Very cool.
Yeah, thank you. Thank you for humoring me.
It is.
I'll pass that around. All righty. All right, well, that's lecture. Any questions about what we talked about? I can literally go hours talking about life, extraterrestrial life, and planetary geology, by the way. Like what you got was not even a taste of the conversations that we could have. Okay, let's pull up your lab here. Again, just like always, your lab PowerPoint it's just like an overview of what we discussed in class. I think it's only like 7 slides. It's 8 slides, right? Not a whole lot here. It's just supposed to be a quick reference guide, okay? So you've got your metamorphic textures, foliation, your slaty foliation, your schistose foliation, your gneissic foliation. You've got stretched grains. That could be a consequence. That is also a foliation. Recrystallization. These are non-foliated textures, okay? So recrystallization, like you get with marble. Fused grains, like what you can get with a quartzite. You can get porphyroblasts as a result of all this, yada, yada. This is kind of the process by which you're going to identify your lab 4 rocks. Is it foliated or non-foliated? If it is foliated, does it have layers? If it is, what size are the grains, right? So on and so forth. Okay. That's it. It's very simple, very easy lab. I promise you they got easier over time, right? Speaking of which, by the way, for my online students, I am caught up as of today, Tuesday, the 4th, grading all of your Go React presentations, but I have not yet finished all your labs. For my in-person students, I finished all the lab 1s that have been turned in, and this morning I got halfway through the lab 2s. I'm going to finish with the lab 2s today and start grading the lab 3s, and I will do my online labs as well today. Fingers crossed. Okay. Any questions about the lab or about anything we discussed today before I end the recording? No? Okay. Well, just make sure that you come next time with questions prepared for our exam review. And for my online students, please make sure that you send me those questions no later than tomorrow night. If you're watching this on Tuesday, that is Wednesday the 5th. Send them to me no later than Wednesday the 5th. If you're watching this way far in the future, ignore those dates.